Now that your brains are completely fried from listening to all that information, we're going to give you some practical applications on the ultrasound machine to help you understand it better. Let's begin with read versus write magnification. Read magnification occurs after freezing. This is post-processing. The sonographer identifies the region of interest and the system reads and displays only the original data. The ROI is not rescanned, so the number of pixels or scan lines is the same as the original image. This creates larger pixels from the information that is already in the scan converter. Spatial resolution is unchanged. Whereas write magnification occurs before freezing. This is part of pre-processing. Write magnification rescans the region of interest and writes new information into the scan converter. This creates a new image with increased spatial resolution by increasing the number of pixels or scan lines in the new ROI. As you can see here, the image on the right, captured using write magnification, has improved spatial resolution. The TGC curve. Sound attenuates more as it travels deeper into the body. Because of this, the ultrasound image becomes progressively darker with increasing depth. This is why compensation is needed. The function of compensation is to produce an image of uniform brightness from top to bottom. We know this as the TGCs, time gain compensation. Here is the anatomy of a typical TGC curve. Superficially, reflections undergo a small, constant amount of compensation called near gain. Delay is the depth where variable compensation begins. Slope is where compensation corrects for the effects of increasing attenuation that result from increasing path length. At knee depth, reflections are maximally compensated for. The far gain continues to compensate the maximum amount. As you can see, the image has a uniform brightness thanks to compensation. Simply put, dynamic range is the amount of shades of gray used to create an image. As you can see here, increasing your dynamic range will create a smoother, clearer image because it is lower contrast. When you decrease the dynamic range, which increases compression, the image displays less shades of gray, appearing more bistable or black and white, creating a rougher image with higher contrast. This is not desirable for our ultrasound images. Harmonic imaging is the creation of an image from sound reflections at twice the frequency of the transmitted sound. Harmonics are created by nonlinear behavior and speed. Most ultrasound machines will already have this feature on, but when we turn it off, we can see why this is so important. This is because harmonic frequency waves undergo less distortion than fundamental sound waves. As you can see, a clearer image is created, but the bottom of the image is partially lost or distorted. This is due to the fact that the strength of tissue harmonics signal builds as the wave travels deeper into the body and then quickly dies down. It is created by the sound beam's main axis, where the beam is strongest. So it is important to try to center the structure you're trying to image. Harmonics are useful especially when you are imaging anechoic structures.